This is integrals, specifically definite integrals. Now the standard properties of definite integrals are given here. They're pretty straightforward, like inverting and a summation and whatnot, but we'll start with defining what we actually are doing when we're integrating something, where a sum, an integral is basically a sum. Think of the integral sign as being a long elongated S to represent the sum of some function or whatever here. Now this is a definite integral here, as it's exact, and this is an approximation between a and b of the same function. This is figure 1, figure 2. There is n sub intervals between a and b. As said, figure 1 is a definite integral. Figure 2 is a collection of n rectangles whose signed area is approximately this definite integral here. The endpoints, or nearest to a of the subintervals, are a plus 0w, a plus 1w, a plus 2w, ... a plus n minus 1w. So an approximate value for the definite integral of f between a and b is this here, or up to f of a plus n minus 1w multiplied by w, which, taking out the factor of w, where it leaves us with this here. Now as the value of n gets larger, the value of the expression gets closer and closer to the value of the definite integral here, of a and b of f of x dx. Where n goes to infinity, it's exact. Now the algebraic definition of a definite integral of x is continuous on a and b are numbers, and a and b are numbers in the domain. Then the integral of f between a and b is given here, where the limit of n goes to infinity of the above function which we have given, where w here is w equals b minus a over n. Now moving on. Now the constant multiple rule and sum rule. For the squared bracket notation, k of the definite integral f of x between a and b equals this, where k is constant. With the sum, we get this here, which is straightforward. Now we're a quick example below. Evaluate the definite integral between 1 and 2 of 1 plus x cubed of dx. Now the fundamental theorem of calculus gives this, the sum rule gives this, the quotient rule gives this, as we've defined up here, which when you go through all that, our exact value is 19 over 4. Now I haven't actually said yet what a definite integral is, have I? But a definite integral is basically any integral what has a value here and a value there. If there's no values, then it's an indefinite integral, so we don't get an exact value. Anyway, moving on. Now the constant multiple rule and sum rule given here. We have an example of this here. And between 0 and pi of the integral here, where what we're integrating between 0 and pi, which is given here on this graph pictorially, and this is the function y equals x plus 2 sine x, then we're going through exactly the same as what we went through before here with these rules, and we, once evaluated, we get to 1/2 pi squared plus 4 here, which is our solution to this. So again, moving on. And another example, integrating a function of a linear expression. This time we're dumping something on the outside of the integral in order to cancel something that's on the inside. So integrating a function of a linear expression. Integral of sine of 5x minus 2 dx. Well, we make the substitution of u equals 5x minus 2, then du by dx equals 5. So our integral becomes this here. And once we substitute in the u, we get this. and doing the integration, we get this. Plugging back in again the values for u, we get this. So that's that example. Now moving on. Now this is the last example. We're going to do one that's slightly more tricky here. It's an integral of 1 over 1 plus 9x squared dx. But really, really we can see that this is just the same as this here, which makes things, simplifies things quite a bit. So here we can make the substitution of u equals 3 of x, so du by dx equals 3. So again we have this 3, so as a 3 we can take the 1/3 outside of the integral here, and then multiply by 3. So we got to think about these as kind of cancelling each other. So upon making a substitution we of u here, and we can do the integral here, which is the inverse tangent, because 1 plus x, the derivative 1 plus x dx equals the inverse tangent of x. So this gives us the inverse tangent of u, because we made that substitution for our value of x here, plus some arbitrary constant of integration. Plugging back in, it's 3 of x here, so plus this arbitrary constant of integration. A quick note, this constant of integration can say, if you're integrating, say basically say if it's something to do with a quadratic, then this constant can be like how far up the axis you are here. If you're here, it's like an intercept, a y-intercept. You can think of it like that, I think. It's been a long time since I've gone over this, many years now, and I think it's along those lines. But you could set c to 0 and you would be sort of at the origin for an x squared sort of function. But that's it for this mini lecture. Please do like and subscribe. I've got a lot more to come. Thanks.